Hey guys, I want to go ahead and continue doing another video. This time on continuous growth. We're just kind of piggybacking on compounding growth, and just to let you know how we derive this. So we start off with our compound formula here, and essentially we're assuming that the rate of growth is 100%. And what happens is this end value here is how many times it's growing or multiplying or compounding. So if we notice, we start off with n equals 1, 2, 4. Okay, so this is the number of times it's being multiplied. So here we would end up with a equals p times 2 to the t power. Well, what happens is when the n value gets very, very large, okay, we approach a certain number called 2.71828, which is essentially E. And what happens is it was developed by discovered by a gentleman named Euler, Leonard Euler, and this is basically the expression. So when we have something that grows continuously, okay, we develop this formula: A equals P, the principal amount, the amount you start with, times e to the RT or KT. Okay, so when we're talking about bacteria, chemical elements that are always continuously either decaying or growing, this is essentially the formula that we use. So K is the growth rate, T is the time, A sub 0, which a professor might use, is the initial value, and then A is the final value. So a lot of times with these problems, you're gonna have to find what we call the growth rate, the K value. Okay, so first, because you're probably going to start off with two unknowns, but essentially with these problems you're going to have to find out the K value, all right, in order to go ahead and solve it. So let's go ahead and see if we can do some of these examples. And I just kind of did the math already behind it, and I'll just explain it. So you have a microbiologist researching a new virus, and they tell us that the initial bacteria is 50. So that means when we start, we have 50 bacteria. So X is always represents time, okay? Because it's independent. You can't control time. It's always continuous. And then the other part is after 5 hours, we have 400 bacteria. So we have this representation. It says find the number of bacteria after 1 day. So then, like the compounding formula, we lay out our variables here that we need. A is what we're trying to find out. A sub 0 is our initial value of 50. K, we don't know. T is 24. Why 24? Because there's 24 hours in a day. So we start off with our stuff that we know here. So we know that we're going to use this point here, or this value here, in order to go ahead and find our K value. So we know that we have 400 bacteria. We start off with 50, okay? E is our growth, not our growth, but E is just our base. K is what we're trying to find out in 5 hours. So this gives us, dividing by 50 on both sides, we get 8. Well, now we have this guy, the K on the top. How are we going to bring it down? We're going to use logarithms, okay? So once we take the natural log on both sides, and you have to use the natural log when you're talking about the base of E, okay? You can bring down the 5K. And remember, ln of V is equal to 1, okay? So now all we got to do is divide by 5, and we get our K factor. Let me move it up. And we get our K factor, okay? So remember, ln of V is 1. So now when we divide, we get this guy here. So that guy is going to be 0.41589, which is great. Now we can finally find our formula, our amount. So we have 50 as our initial. We have our K value times 24. Put that in the calculator, and that gives you the number of viruses after 1 day. Okay, guys, so with these problems, you're going to have to find out the K value first. Let's go ahead and see if we can do another problem here. A certain bacteria doubles every 4.5 hours. If you start off with 200 bacteria, how many bacteria will there be in 2 days? Again, we start off with our formula here. We start with our values here. A, we don't know. A sub 0 is 200. Our K value, we got to figure it out. And T is 48. Why 48? Because you have 2 days. Now, initially you're thinking, well, how am I going to figure it out? Well, the key is when it says it doubles. Notice how I wrote this out here. We have an initial amount. We don't know what that is, but we know that it doubles. So whatever this guy is, it's always going to be twice. So a sub 0, and this is going to be twice a sub 0. And what you're going to do is you're going to divide both sides by a sub 0, and these are going to simplify out. Okay? And so essentially you're doing this because you're dividing. And you're left with this representation. Well, again, now how do we get this guy down? Well, we use the natural log. Why? Because we have a base of e. So ln of 2 times equals ln of e. Bring the 4.5k down. Remember, ln of e is 1, so now you have 4.5k. Divide by 4.5, and this is your k factor. Now that we have this guy, we can go ahead and figure out the amount. So 200 is our initial. E, here's our k value, 48 hours, calculator, and we got it. Okay, so notice when the bacteria doubles, it's just twice of whatever this guy is. So 2a sub naught equals a sub naught. So these two are going to simplify out. All right, let's do another one, guys. 2 more. We have a certain radioisotope that has a half-life of 8 minutes. Find its decay constant, or its decay rate. Again, we start off with our initial formula. We have a sub naught, we don't know. We have k, which we're trying to figure out, and t is equal to 8 because it's 8 minutes. Well, it says the half-life is 8 minutes. So that means that when t equals 8, we're going to have half of the original amount. And similarly, like the previous problem, these two are going to cancel out. So we're left with 1/2 equals e to the 8k. Well, what do we do now? Well, we take the natural log on both sides. The 8k comes down. Ln of e is equal to 1. So now we have this expression. So we divide by 8. If we get ln of 1/2 divided by 8. And there we have our decay rate. Okay, so notice how I did that. Half-life is equal to 8 minutes. That means half of the original. Okay, I don't know what that is, but I just know it's going to be half of the same thing is equal to, it takes 8 minutes. So because these are the same, you're dividing. Remember, you're dividing, so these guys are going to cancel out into a 1, and you're left with this. Use your logarithm properties, and you're able to get your k rate. Last one, guys. It says radioactive decay rate of an element is this value here. If you start with an initial amount, how long before the half of the element is decayed? So, same thing. We start off with our formula. We don't know the initial amount. We don't know the the final amount. We do know the k rate, but we don't know how long it's going to take. That's what we're trying to figure out. Well, much like number 3, okay, all we know is that whatever the initial amount, we're going to have half of it because it says how long before half of the element is decayed. Well, they gave us the k rate here. So now we have the a sub naughts canceling out. We have the 1/2. We take the natural log on both sides again. This guy comes down. Remember, now we have ln of v. ln of v becomes a 1. So now we have this value here. Well, we divide by the decimal and put it in our calculator, and we end up with 16, a little over, almost 17 minutes. So hopefully that helps, guys. Let me know if you need me to do more problems. Till next time.